Hi, class. So this is our last lecture in chapter 20 and also the last lecture in our course. And so this lecture is going to focus on polarity in organic compounds, and we will pay particular attention to the polarity in functional groups. That's how polarity occurs in organic compounds. And we'll be doing worksheets 40 and 41. And so I'm going to share my screen. And here we go. So the learning goals in this chapter, or this lecture, will be to review polarity in covalent compounds, and that it should be review. In fact, most of this will be review. Polarity in covalent compounds you can find in chapter 7.2, and then we'll look at the polarity in functional groups. And then by understanding polarity in functional groups, we'll apply that to the polarity we find in organic compounds. And remember, polarity goes from nonpolar substances all the way to polar or ionic substances. And then finally, we'll look at intermolecular forces. These are forces that hold molecules together, and they're distinct from bonding, covalent bonds, although one of them is called a hydrogen bond. It's not really a bond. It's a strong electrostatic attractive force. So that's what these are. These are electrostatic attractive forces that hold molecules together, but are much weaker than covalent bonds or ionic bonds. So these are called intermolecular forces between molecules. Intramolecular forces are what you would call a chemical bond. That's within a molecule. And let's change slide. So electronegativity, bond polarity. Well, that comes from the electronegativity of the atoms that are bonded together. And this is a periodic table that shows electronegativities of all the different atoms when they are bonded together. And the lowest electronegativities are down here on the left, the lower left of the periodic table. The highest electronegativities are in the upper right. And you notice we don't include electronegativities for the inert gases. That's because they don't typically form covalent, or they don't form bonds, chemical bonds with other atoms. And so the highest electronegativity, it's not hydrogen up here. Hydrogen's 2.1. It's here, it's fluorine. Fluorine is the element with the highest electronegativity. So this table shows the electronegativity classes, if you will, the polarity classes based on electronegativities of the atoms that are bonded. And roughly, we see the electronegativity difference. This is from the electronegativity difference. And by that, I mean, what I write, you can try to draw a delta on here on the screen. The delta means the difference. That's the difference in the electronegativity of the two atoms that are bonded. And what I usually do is take the higher electronegativity and subtract the lower electronegativity, so you always get a positive value. And those values come off of that table, the table I showed just previously. So you can have an electronegativity difference equal to 0. And an electronegativity difference of 0 from a carbon-carbon bond. So you subtract the electronegativities of one carbon from the other and you get 0, okay? That's called a pure covalent bond. If the electronegativity is not 0, then you've got a covalent bond. And we have different covalent bonds. We have non-polar covalent bonds and polar covalent bonds. And we'll look at those in a minute. If you have a huge electronegativity difference, say between a metal and a non-metal, you'll get an ionic bond. And usually what we're talking about in organic compounds, we're talking about about covalent bonds, pure covalent bonds, non-polar covalent bonds, and polar covalent bonds. So on the right, it shows how you distinguish between these classes of polarities in chemical bonds by the electronegativity difference. And this scale is arbitrary, somewhat arbitrary. And in your book, it has less than 0.4 is called I would call this a non-polar covalent bond, not a pure covalent bond, but a non-polar. A pure covalent bond is non-polar. Non-polar, let me write that down. So if it's 0, it's a pure covalent bond. If it's less than 0.4, it's a non-polar covalent bond. The polar covalent bond then is between 0.4 and 1.8. And an ionic bond is an electronegativity difference greater than 1.8. And like I say, these are arbitraries. If you look in different textbooks, they're slightly different, but this is okay. I have some examples down below. Let's see. As electronegativity difference increases between the bond becomes increasingly more polar, and that would be as if we go down this is increasing polarity. If the electronegativities are different, so if it's anything but a pure covalent bond, it has a dipole. So even non-polar covalent have dipoles. They're weak dipoles. So dipoles have terminology that goes from weak dipoles to strong dipoles. The strongest dipoles are the bonds that have the largest delta En. So here's an example of some bond. So I have a carbon-carbon bond, that's 0. The atoms don't have to be the same. They have 0. Carbon and sulfur have both. The next one is carbon and sulfur. Carbon and sulfur both have the same electronegativity value. So 2.5 minus 2.5 gives you 0. Carbon and bromine have a very small difference. Let's see, carbon is 2.5, I guess bromine is 2.8, so you get a 0.3 difference. Carbon and hydrogen have a 0.4 difference. Nitrogen and hydrogen, 0.5. Carbon with a double bond nitrogen. Now, I put a few double bonded atoms in here, so it doesn't matter if you have a single, double, or triple bond. The electronegativity difference is just the difference between the atoms. So nitrogen is 3.0, and carbon is 2.5. So this should be 0.5, not 0.9. I'm not sure why it's 0.9. Oh, these are switched. These are switched. The NH, sorry, this should be this. The NA. These are flipped. So the CN is 0.5 and the NH is 0.9. We go up to a CO bond. And like I said, it doesn't matter if you have a double bond. CO is 1, C double bond O is also 1. OH is 1.4, and ONA is 2.6, so that's the highest. And this is ionic. So if we wanted to break this down, we said non-polar covalent bonds, pure or non-polar. Well, let's see. These are pure covalent bonds. 0.8 is a non-covalent bond. 0.4 to 1.4 are polar covalent bonds. And then up here is the last one, 2.6 is an ionic bond. We said that all bonds, they have a difference in electronegativity have a dipole. And that's what this shows. This shows a bond HCl with a dipole. And distribution, what that means is the distribution of the electron density in the bond is uneven. So the element with the highest electronegativity pulls the electrons in that bond toward it, so it has a higher electron density. That's between around the chlorine atom. So the electron density, the electronegativity of chlorine is 3.0, and the electronegativity of hydrogen 2.1. And so electrons are going towards the chlorine, which is increased electron density around the kind of a bigger sphere, bigger circle. So the symbols delta plus and delta minus indicate the polarity of the HCl bond. So because there is a greater electron density around the chlorine, we could say that's a partial negative charge. So it's not a full negative charge like a chloride ion, but it has more electrons, pulled some of the electrons to it. There's greater electron density than the hydrogen. So the chlorine becomes partially negative. We represent that with a delta minus, and the hydrogen becomes a partially positive, and we represent that with a delta plus. And then lastly, we show an arrow pointing to the chlorine, and that arrow shows a dipole, symbol used for showing dipoles. So that shows the dipole in that bond. And since HCl is a molecule, that's a dipole in the molecule also. Later on, we're going to talk about intermolecular forces. I mentioned that previously. And molecules with dipoles have kind of strong, they have this dipole-dipole attraction. So you can imagine if you have one HCl with a delta plus and a delta minus, and you have another HCl that looks like this, ClH. So here's the delta plus here, here's the delta minus here. Well, you get attractive forces between the pluses and the minus, and those molecules stick together pretty well. And that's the electrostatic attraction that you get in intermolecular force. We'll see that, we'll explore that more later on in this lecture. So how does this polarity in bonds translate to polarity in molecules? Well, in HCl, it's pretty simple, it's straightforward. But in molecules, you have to consider the polarity of the bonds, and most molecules have more than just one bond. Okay, so you have to consider the polarity in all the bonds. You have to consider the type of bond. If it's a, whether it's nonpolar, and whether, it's a pure covalent, it's nonpolar, or it's highly polar, strong covalent bond. You also have to consider the shape of the molecule. So if it's a linear molecule, oftentimes, even if it has polar bonds and they're both the same, in a linear molecule, the polarities, the dipoles cancel. And so the molecule itself can be nonpolar. So that's pretty common. It's not rare where a molecule will have polar bonds. A molecule contains polar bonds, but the molecule itself is nonpolar. And that is because of the shape of the molecule, and all dipoles cancel. So here's some examples of dipoles and non-dipoles in molecules. So if you look at borane on the left, HB bond, let's look at this top row here, the top row. These are non-dipole. These are molecules that don't have dipole. So the BH bond is actually weakly polar bond. So let's see, the boron has a electronegativity of 2. Hydrogen is 2.1. So you only get a delta En of 0.1 here. So the hydrogen might be partially negative, and the boron is partially positive. It's very weak. Now, is that boron has a trigonal planar structure. So even though it has very weak dipoles, all the dipoles cancel because they're all in equal and opposite directions. So even if the BH had a strong dipole, it would still be nonpolar. Sorry. So let's look at CH4. So CH4 is tetrahedral. The CH bond is 0.4. So that in our scale, that was called a polar covalent bond. But CH4, the dipole then would go from carbon has a little bit higher electronegativity than hydrogen. So the dipole goes from, the bond dipole goes from hydrogen towards carbon. If there's 4 of them, all pointing towards the carbon, all these dipoles cancel because they're equal and opposite in direction. And so dipoles are kind of like in a molecule, are kind of like a tug of war for all the bonding electrons. And you can see if they're all pushing in equal opposite direction, they get canceled out. Here's a benzene ring. Now the thing about benzene ring, it's flat. Again, it has CH bonds, it has CC bonds and CH bonds. Well, the CC bonds have a pure covalent bonds. They don't have any dipole at all. The CH bonds have a slight dipole, but again, they're all laid out in equal and opposite directions. There's a lot of symmetry in this molecule. It's a planar molecule. And so all those dipoles cancel out too. So that's nonpolar. The last molecule here, CO2. CO2 has really polar bonds. Carbon-oxygen bond is a very polar covalent bond. It would be considered one of the stronger polar covalent bonds. And it's a linear molecule. CO2 is linear. Here's the dipoles. I have the dipoles shown. Well, those dipoles, you can tell, cancel out. And so that makes CO2 a nonpolar. If CO2 was not linear, it would definitely be a polar molecule. So let's look at these other molecules at the bottom that are polar. These have dipoles. So in the case of the BH3, we substituted one of the hydrogens with a bromine, and the bromine has a electronegativity of 2.8. Boron is 2. So we have a 0.8 difference, a delta En of 0.8 right here along this boron-bromine bond. So we've got a dipole there. The BH bonds have weak dipoles. So this whole molecule is, the electrons in this whole molecule are being pulled towards the bromine. So we've got a big dipole going from the bottom of this molecule up towards the bromine. Okay, we don't have symmetrical electronegativities now around the boron. The B-Br bond has a much greater polarity. I should say the polarity of the bonds, covalent bonds around the boron, are not all the same. And the same goes with the CH3Cl. We've distorted the electron distribution by adding a polar CCl bond here. And so the dipole in this molecule then goes from the carbon side or the hydrogen side, which is like the nonpolar side, towards the chlorine. Go over to our benzene ring where we've removed hydrogen and substituted an OH. OH is a very polar bond. If you remember, OH is one of the most, it's the most polar bond we find in